online on our website. Feel free to check it out if you want to revisit or if you have to leave early. So a brief introduction on Juan Pablo, our wonderful presenter today. So Juan Pablo is a fifth-year PhD student in health services research at the Institute of Health Policy Management and Evaluation, and a biostatistician at the University Health Network Biostatistics Research Unit. His research interests lie primarily in multi-state modeling and evidence synthesis, and his thesis research is on developing and applying Bayesian methods to health technology assessment. So thank you, Juan Pablo, for giving us this workshop today.
Yeah, hi. Hi everyone. So I see some of I know I would say half of the participants, so that's good. So so yeah, so as Juan mentioned, I'm Juan Pablo, and today we're gonna talk about a Bayesian meta-analysis. Let me just share my screen, and we'll go from there. Okay, so this workshop that I prepared today is similar to the one this year Juan invited me to as a guest lecturer to her Bayesian applying Bayesian methods in healthcare research course. I for 3 hours I talked about this topic. So this is the material, and it was, I think it was 2 weeks ago, 2 or 3 weeks ago. So it's recent, and yeah, as Juan mentioned when she was talking about me, one of my research areas is evidence synthesis, right? And probably it's because or mostly because I did my master's at McMaster, and well, McMaster is well known for evidence, well, evidence-based medicine and therefore evidence synthesis. So yeah, I've been interested, especially in meta-analysis in the last probably 5 years, and today we're gonna try to learn a little bit about, or just a little bit about a small background about what's a meta-analysis and why Bayesian, and then we're gonna see the relationship between generalized linear models and a meta-analysis. So basically, what I'm trying to say is that a meta-analysis doesn't matter the inference that if it's maximizing the likelihood or Bayesian. It can be seen as a generalized linear model. So yeah, most of you know, and if you don't, meta-analysis is the idea behind meta-analysis to pull all the evidence from independent sources. And traditionally, this has been done using only RCTs, randomized controlled trials. And we know why the reason behind why RCTs are like or one of the best evidence that we can find in healthcare research. So traditionally, meta-analyses are done only in using RCTs, and because of the possible the confounding that it's I wouldn't say removed, but minimized. But now there is new, like probably in the last, again, 5 years, there are new methods for meta-analysis in the context of observational studies. Probably you have heard about this meta-analysis. More broadly speaking, there in meta-analysis there are two models, and one model is called the fixed effect model, and the other one is the random effects model. So probably you have heard about these two terms in meta-analysis, but basically a fixed effect model assumes that a single parameter value is common to all studies, and we're gonna see it in a little bit. What does this mean? And a random effects model that parameters underlying studies follow some distribution. So again, I'm gonna when we see the model and we see the Bayesian approach, I'm gonna come back to these two models. Nowadays, it's more common to open R or open even even Stata or SAS. It's because of software advances. Well, it's easier to perform meta-analysis on your computer, and that's good, right? Because stuff that was really difficult to be done in a computer 10 or 15 years ago. Well, now because of the software advances, we have seen an improvement, I would say, in computational time, especially like stuff that took forever to be done 10 or 15 years ago. Now it takes probably a couple of minutes. So so that's why I think it's one of the reasons why meta-analysis has its importance has increased in the probably last 5 years, because more people are capable of performing one. And as I mentioned in my learning objectives, the framework, we're gonna see how a meta-analysis can be seen as a generalized linear model, right? And we're gonna see it also as a hierarchical model, because the idea behind the meta-analysis comes from an inherent hierarchical structure, and that's we're gonna speak a little bit more in a bit. And as I mentioned, GLMs, generalized linear models, probably you have, if you took Biostats 2, you do a lot of GLMs there. Even Biostats 1, I think you do a lot of GLMs. And yeah, you have a model and you have parameters. You wanna fit the model in order to see what's the maximum likelihood estimate for these parameters in your GLM. That's from the, if we can call it, frequentist approach. But also the same. There is it can be also you can learn from the data with a GLM under a Bayesian context. Okay. So this is the way. So this theta hat represents the effect. So the idea, as I mentioned at the beginning, right? We have the idea of the meta-analysis is to pull the evidence. How are we gonna pull the evidence? Okay, so for each study that meta-analysis always is I would say a second part of a systematic review. Usually a systematic review and meta-analysis come together. At least from the evidence-based medicine side. So usually for each study that is going to be included in your meta-analysis, you will have for each study an effect size. So for example, if the study is let's say the study reports, for example, hazard ratio will be the effect size, or mean difference in any blood test level, that would be our effect size, or mortality, right, which is a count, how many out of n patients, how many were dead at the end of the study, right? So that will be for each study. We will have that effect size, and we will have the uncertainty associated with that effect size. So the uncertainty associated to that effect size is the standard error of the effect size. Okay, so the traditional methods, basically what they do is that the fixed effects model basically is this yi represents the effect size, and I will be the study. For each I study that we have, basically, the fixed effects models, this theta hat is our best guess of the mean effect size, right? So under a fixed effect model, what we're doing is we're basically weighting, right? Where these W's are the inverse of the variance. or the uncertainty associated that I talked about when we're collecting data for our meta-analysis, right? So basically what we're doing here, the mean effect size, our best guess in traditional meta-analysis, if we assume that we're using a fixed effect model, our best guess, the mean effect size, will be only a weight, right? The sum of the weight of each effect size, and the weight will be given by the standard error of this effect size, or the variance of this effect size, the uncertainty associated, right? So then you can see the more uncertainty you have, what will happen, and on the other way, if the uncertainty is not that bad, meaning that the variance is smaller, what's the impact on this weight, right? Now, under a maximum likelihood approach, frequentist approach, the random effects model, model on the other side is the same structure for our best guess, the mean effect size, right? But now what is going to change is going to be this W, the weight for each study, right? So this new W on the random effects model will be, again, the inverse of the variance of each study, the uncertainty surrounding this effect size, plus another parameter tau, which is going to be our best guess of tau, a square of that, which will be this represents the between study heterogeneity, right? So we have the weight is going to be what we have on the fixed effects models, but now you're going to add another value that will represent the between study heterogeneity, right? So you can see that if the between I usually, when people know me, I usually try to make the audience talk to me. So I usually make questions, right? So one of my questions is, what do you think will happen if this tau, if the estimate, our best guess of tau, the between study variance, it's really huge in terms of the VI, which is the variance, the standard error of our effect size for each study. What happens to VI when VI, the variance, the standard error variance of each effect size for each study, when this tau, it's huge, huge compared to each VI individually. Anyone? So the difference between the fixed and random effects model is when there is a lot of between study heterogeneity, when this tau is gigantic compared to this VI, basically this VI disappear, right? They're gonna be really, really small, and the ratio and the weight is gonna be basically given by the between study heterogeneity that was estimated from the data, right? So what does it how this is translated to clinical practice? If we have a lot of it between in our meta-analysis, a lot of between study heterogeneity, that will mean that our effect sizes, if we have a forest plot, our effect sizes will be of our studies will be all over the place. Some of them will be positive, some of them will be negative, some of them around zero, yada yada yada, right? That graphically, that will mean like it will mean that we have a lot of heterogeneity in our effect sizes in the meta-analysis that we're trying to perform. Okay, that will mean if we take a random effects model, that the weight, remember that our best guess, our mean effect size, is the weight of each effect size, the sum of the weights of each effect size, and we saw that if this is gigantic and this VI is really small, then it won't matter if our study has thousands and thousands of patients, right? Even though if we, as we know, as we increase the sample size, we reduce, or we get closer to the truth that we're trying to estimate. So under a random effects models, even though we have decent sample sizes in our studies, meaning that our variance, it's the uncertainty surrounding the estimate is really small, then on the random effects model, this disappears, right? This, or more than disappearing, it won't have an impact anymore, right? On the other hand, if this tau is really small, that will imply that as we see this, when this tau is 0, this implies the random effects model transforms to the fixed effects model, right? So if this tau, the between study heterogeneity, is really small, then the variance, the uncertainty of each effect size will have an important. It will have an important. It will be more important. Sorry, a more important weight. And as you can see, as this tau goes to 0, right, the tau gets smaller. There's not that much between the heterogeneity. Then the random effects transform to the fixed effects. Okay. What you're probably wondering, why are you talking about this? Well, this will have an impact in when we talk about the Bayesian weight, and you will see how much similar they are, right? How much similarities they share. The traditional way, and if you have done meta-analysis, for example, in R, this is the idea behind of the basic models, for example, in the library Meta or Meta4, right? And you will see how I want to talk about this, because you will see how related they are to the Bayesian method, to the Bayesian way to do this. And from the evidence-based medicines, they say if you have a lot of between study heterogeneity, then you shouldn't pull, right? Not even, you shouldn't even use a random effects model. You shouldn't pull, because that means that clinically speaking, your studies are the population in your, or there's probably a high chance that the population in each study is completely different to the one that you structure in your research question, right? And that's from the evidence-based medicine. Okay. Side. And there was they in the past they have because this tau is an estimate, then you can also do hypothesis testing, right? And in the past they used to test it, right, from in the traditional way, if this was 0 or different than 0, but that's not recommended anymore. Okay, so this is basically how meta-analysis is done from a frequentist point of view, right? We have two models, fixed effects, random effects models. We see that the idea of meta-analysis is pulling the evidence. So for each study, we will have a effect size, and we're gonna try to estimate a mean effect size, right? And this effect size could be hazard ratios, odds ratios, mean difference, risk difference, any effect size that you can think about. Okay. Now, Bayesian. I'm not gonna get, this is not a workshop about Bayesian statistics, so I'm gonna go really quick about Bayesian inference. So the whole idea of recent and especially applied Bayesian methods is to sample from the posterior, right? So that's the whole idea, at least if you're doing applied Bayesian statistics or by applied Bayesian biostatistics, and you have a statistical model, most likely you will need to sample from the posterior. And one way to sample from the posterior are the Markov chain Monte Carlo methods. And there are different algorithms behind these MCMC methods. One of the most I think famous one, and I would say one of the earliest, probably like I think it's 40, 50, or even 50, 60 years ago, is Gibbs sampling. Then you have a combination of Gibbs sampling with something else. And recently, in the last 10 years, that has been there has been an increase of the use of STAN. STAN is a probabilistic programming language, which is suitable for Bayesian statistics, because the algorithm behind STAN is the hybrid or Hamiltonian Monte Carlo, which is an MCMC method, and basically a STAN follows. If you have ever used JAX before, a STAN has its syntax is similar to JAX, right? So basically, yes, if you want to do Bayesian inference, you have to sample from the posterior, and there's some tools, some probabilistic programming languages such as STAN, and that can be, if you are an R user, STAN and R have a lot of libraries and a lot of, you can access STAN through R. And therefore, yes, we have to sample. If we want to take a Bayesian approach, we have to sample from the posterior. In order to sample from the posterior, we have to define our model, our statistical model, right? So right now, and probably today, we'll talk about how the model behind a continuous, when we have continuous data. But as I mentioned, meta-analysis can be seen as a GLM, and therefore we can have other, we can perform other types of meta-analysis of a meta-analysis, not only for continuous data. We can have binary data, and I won't have to talk about that today, but for any type of data, if this model can be seen as a GLM, therefore we will be able to perform a meta-analysis given the type of data that we have. For today, we're only gonna cover continuous data. Okay, so same as before, yi is gonna represent the effect size, right? So for the idea behind doing Bayesian inference is that we will have data, right? We have data, we want to learn from there. So we're gonna, that this also applies to from a frequentist or maximum likelihood approach point of view. But the idea is we will have a statistical model, right? We're assuming that our data was generated by some statistical model. So for continuous data meta-analysis, this applies. This is exactly the same. These first two lines here are exactly the same from either a frequentist or Bayesian approach. What it changes is just the uncertainty about the parameter, right? So I have data, and because I have data, I'm assuming that they come. There's a statistical model that is generating this data, right? What's this statistical model that I think the data was generated from? So what I'm assuming is that each effect size I represents the study I, right? Given when I do my systematic review, I found that I have I studies, and that will be part of my meta-analysis. So for each effect size, or I assume that each effect size comes from a normal distribution with a mean that will be for each study. So it's not going to be a common mean for all the observed effect sizes. Here, what we're assuming is that each effect size comes from a normal distribution that will have its own mean. Each study will have its own mean, and its own standard error. Now, the difference here is this sigma squared yi is the standard error or the variance of the effect size. So this is not a parameter. This is given, right? This is given, and it's exactly the same as as this approach when you're trying to construct confidence intervals for these, our best guesses, our estimates. Assuming normality, this will be equivalent to the Bayesian approach. And basically, what I'm saying, as I mentioned before, what I'm saying is that each effect size comes from a normal distribution with its own mean and its own standard error, and this standard error is the uncertainty behind each effect size for each study. Okay, now the next part is, and this is for the random effects model, is that each theta I, which is the mean effect size for this for the study I, comes from a normal distribution now with a common mean and a common sigma square, a common variance, or a common standard deviation, right? So basically what I'm saying is that each study comes from a normal distribution with its own mean and its own standard error. And each mean, this theta I, comes from a normal distribution, but with a common mu and a common sigma square, common variance. Now, the difference between Bayesian and traditional approaches is that Bayesian statistics quantifies the uncertainty with probability, and at least from a parametric Bayesian statistics point of view, therefore we will need some prior distributions to the hyperparameter, which is this mu and this sigma square, right? Because if we know mu and sigma square, we know theta I, and if we know theta I, we know we could generate the data that was given by us, right? So the parameters that needs to be estimated are the mean effect size mu and the between study variance. Same as the frequentist approach. Let's go back. Mean effect size theta hat, and on the random effects model, tau square hat. That's same as here, two parameters to estimate, frequentist and Bayesian, right? Mu is going to be our mean effect size, and this will be the between study heterogeneity. Questions so far? Oh, okay. So this is random effects model. A fixed effects model assumes that this is equals to 0. So, right? Meaning that there is no a fixed effect, there is no between study heterogeneity, and that all studies share only one single true effect size, meaning that theta I will be equal to mu. So you can see here the hierarchical structure of the model, right? And it's like a GLM, right? We have our outcome, yi. We assume that our outcome is generated by some distribution, which in this case is the normal distribution. And the normal distribution has two parameters, the mean and standard deviation, mean and variance. In this case, the mean will be, each study will have its own mean, and the standard deviation associated to that, this theta I, is the observed one, the one that we have from our studies, the uncertainty that we just talked about. And then we can see here the hierarchy, right? We're assuming that this means for each study I come from a normal distribution, again, two parameters, but now common mu, a common standard deviation. Okay, so this is our model, and in order to do apply Bayesian statistics, we have to translate that into code. Today we're gonna see briefly a library in R, which is called BRMS, and BRMS is a library that uses stan in its background, but has the same syntax as LM, LME4. All these generalized linear models that syntax from R, right? So it's really straightforward to do it. As I mentioned, under a Bayesian approach, we need priors. We're gonna use the ones that we're gonna see which ones are the ones that BRMS gives to you. By default, BRMS gives weekly informative priors. I'm not gonna get into that, but you can see more information in this link. And this is the explanation behind why BRMS calls it weekly informative. Okay. So in BRMS, yes, Osvaldo.
Thanks, Pablo. So this is more of a, I guess, I don't know, philosophical question, I guess. So even though you're mentioning that the fixed effects model is a special case on the, the model that you're outlining here. So in practice, unless you specify like a prior with only a point mass at 0 or something like that, you would get to that fixed effects model, right? I mean, otherwise,
Yeah, no.
I don't see.
In practice, is this theta I is not a stochastic relationship anymore. It's just yeah, it's just you don't have this hierarchy, right? You have you basically delete all of this second line, and you, instead of theta I, you only use mu.
Oh, right? I see. So if you really wanted to fit like a fixed effect,
yeah. So
yeah, I see.
Yeah, a fixed effects. This one. So this is the generative model under a random effects model. Under a fixed effect model, this, I will say, this line right here disappears, and this theta I is going to be now mu, right? You still have, and now you only have prior on mu. You don't need a prior on, you don't need a prior on sigma squared of theta, because, well, that's not a parameter anymore. Yeah,
I see. Okay, yeah, that makes sense. Okay, thanks.
Okay, no problem. So yeah, so fitting a Bayesian meta-analysis using BRMS. So meta-analyses are somewhat special because we do not have a variable predicting effect size, right? Also, we have mentioned that this is we're going to, if we have time, I don't think we'll have time, but in my notes the notes that Juan share, I talk about meta-regression, and basically meta-regression is including study level covariates in order to explain some of the between study variants. And as I mentioned, meta-analysis is GLM. It can be seen as GLM, and in GLM we have covariates, right? So we can include these study level covariates, and it's called meta-regression. And it's also special compared to GLMs. It's also special because the variance, as I mentioned, the variance of the observed effect size is known, right? So we know it. So this, how can be this done in BRMS? So in BRMS, you will follow, I will highlight this one here, but this is exactly the same syntax that LM in R or LME, the library LME4 uses for performing their regression models, right? So what basically the idea behind if we're using BRMS, why would represent in your data frame your outcome, right? I have some code, I'll show it in a bit. And if you want, we can also go quickly, if we have time, quickly through R, but I have the code a little bit down. So why represent the outcome in our data frame? SE is a special function from BRMS to specify that we have observed the standard errors for each Y, and SEY will be the variable in our data frame that represents the standard error, right? So if we have the variance of the effect size, we will have to take the square root of that in order to have the standard error, and then the same syntax as LM, right? An intercept 1 plus the random effect, what they call the random effect, or is a local intercept that will depend on each study. This random will be the variable that represents your in your data frame your study. So we're gonna see an example. This data comes from the library Metaphor. It's a meta-analysis to examine the overall effectiveness of BCG vaccine for preventing tuberculosis, and to examine moderators, covariates that may potentially influence the size of the effect. This, okay, so probably you're gonna see, as you can see here, each row represents the study. We have the year, we have the author. Now, this data comes from T-post to CNET, right here. This data comes as binary, right? Because it's telling you how many positive to tuberculosis were under the treatment, BCG vaccine, and how many positive and negative we have under control in the RCTs that were included for this meta-analysis. So, as I mentioned, we can directly model binary data, but right now, because we have to assume that is continuous, or we're working with a continuous model under a continuous model that works for continuous data, we have to transform this data to some continuous effect size. So one way to do it is the same library metaphor. What they do and what it has been done in the past is, well, you can transform this as log risk ratios, right? The risk ratio is basically the probability of treatment over the probability of control, or the other way, doesn't matter. And you can transform it into log risk ratios in order to in order to remove that, because risk ratios only goes from 0 to really any positive number, right? So what the log does is that it maps that 0 to any positive number to a number that can be also negative, right? So what they do, metaphor, probably if you have done meta-analysis, has this function called scalc that transform your data. So you assign it will create a data frame data frame for you. And probably from here, I'm gonna stop and go to my R code so it becomes clearer. And I'm gonna try to make it bigger. So yeah, we have, I run the data. So this is, I'm gonna run this chunk of code, right? In order that BCG, it's the name of the data frame that it's in the library metaphor. So if we do, oh, sorry, first let me just run my libraries. Otherwise, it's gonna be a problem. Sorry. Okay. So if we do question mark dot BCG, so it's the data, it's in the library metaphor, and it explains more about the data, right? So I'm just gonna assign it to an object called dat, right? And as I mentioned, the function scalc is part also of metaphor, and basically you tell them which one are the this is a contingency table, right? Which ones are the positive, negative for treatment, and for control, the data that where these names are coming from, and the measure that you want to calculate. So you have risk ratios, but we can also do odds ratios, and you can do other effect sizes, basically. So we're gonna work with risk ratios right now. Okay, and we can run now the metaphor. If you have used metaphor, this is the function to run a random effects model under a frequentist approach. Let's look at the data to see what was added from the original data set. So the original data set ended at the variable alloc, but now the function scalc gave you 2 more columns, which is yi and vi, and this is the effect size, right? The effect size, this is the log risk ratio, right? For treatment versus control, and this is the variance surrounding this estimate, right? And these are the two columns that we're going to use in both frequentist and Bayesian approach. So this is how you do it in metaphor. So you use RMA, specify the data, which one is yi, vi, if you want to give the study a label for your studies, and you can print a forest plot, right? So the forest plot under metaphor will look like this, right? So this is the effect size for each study, right? We have the mean effect size. Here I'm not showing what was the estimate of the between study variance, but if we saw it in our R console, we will see here that it's here, tau square. Our best estimate is this 0.31. Okay. And it gives you other measures, such as the the I square and yada, 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 right? And our estimate was minus 0.71. This is the mean effect size between tuberculosis and control. And this is, remember, a log risk ratio mean effect size. So if we want to transform into a risk ratio, we just have to do the exponential of this. Okay. Now, this is under frequentist approach. Now, if we want to do this under BRMS, the function is called BRM. It's the same structure. We have a parameter, an argument that tells you which one is the data frame, what family we're assuming the data is generated from. So this, and we're gonna for the normal distribution, it's Gaussian, and we can I talk about that in the model. Now, this is the formula that we're gonna use in order to run our Bayesian random effects model. So I remember in our data frame, the observed effect sizes is the name of that variable is yi. This given symbol, and we're gonna, this is only to specify, this one right here is to specify that the standard error, we know the standard errors, and that are the square root of bi, and bi again, it's a variable of my data frame. And this will give us this is a columns of 1, which will be the intercept, the mean effect size, and this is what we're telling BRMS, that we will have a local intercept or a random effect for each study, right? And study is the you can use it. You can use trial. You can use study. Doesn't matter. It's just how are you identifying the local intercept for each in your model. And then you have other parameters regarding the MCMC procedure. So you can specify how much you're going to warm up until you start taking into account your samples, how many iterations you're going to run, how many chains, and other stuff from BRMS. Okay. So you run it. I'm not gonna. It doesn't take that much, but well, if you run it, I don't know why it's asking me that. Sorry, I shouldn't have run it. It doesn't take that much. Anywho, meanwhile it's running. This is gonna be your output from that BRMS object, and you will have an intercept, which is the mean effect size. See that it was minus 0.72 on the Bayesian approach and minus 0.71 on the frequentist approach. Sorry, and now you will have this SD intercept is the between study variance. Sorry, but the between study standard deviation, right? This 0.64. Right, and the uncertainty, the credible interval for this 64. So as you can see, it is straightforward. It is straightforward to run a Bayesian meta-analysis in BRMS. If you want to run a fixed effects model, well, you have to delete it because we don't have the random effects part anymore, right? So if you want to run a fixed effects model, this will be the syntax. As I mentioned, you can in my notes, you can directly model other type of data, and yeah, basically, especially for evidence synthesis, and that will be with this I will end. What especially for meta-analysis, but why being Bayesian in meta-analysis? Because I think especially from the evidence-based medicine side of view, I think the priors plays an important factor in a meta-analysis model, and a lot of you can do sensitivity analysis under these priors, and you can use clinical judgment, right? You can get from other meta-analysis you can construct priors that come from previous evidence under similar research question. And yeah, I think that will be it.
Oh, thank you, Juan Pablo. I have a quick question and open to the floor if anyone has any other questions. So just kind of like a quick pointer to us who wanted to maybe consider doing a meta regression where we assume or hypothesize there will be a covariates that affect the
effect size.
mean
Well,
effect size as well as the random effect that is also determined by by certain covariates. Like this covariates could be, you know, quality of the studies.
For example,
some studies are more nicely done, and then you have more confidence in their results.
So yeah, for example, one of them could be, and they've done it, meta regression is done using that one with risk of bias, right? So risk of bias is basically like how for each study you can have a risk of bias and it's basically the quality of the study. So yeah, exactly. You can include these covariates, and it's really straightforward in BRMS. So for example, under the same data frame that we have, the same data that we saw that the allocation or the ablat can be a covariate. This is ablat was the absolute latitude of the study location, right? So if you think the latitude of the study location, it plays an important factor or explains some of the between study variance, right? You can include it really straightforward in BRMS. In my notes, if you go down, this is under R, but if you go down in my notes, you will see this is not meta regression. Yeah. So basically, this is the code for meta regression under metaphor, right? The frequentist, and you only include the covariate. And under BRMS is just here. It's exactly the same code. You just add same structure as LM, right? LM or LME4, right? And then you can run this model, and you can see how much the variance change, right? So how much this estimate change. So without this ablat covariate, we have an estimate. Our mean estimate of this of the between study variance was between study standard deviation, because it's the standard deviation, not the variance. Without that covariate, our best guess was, and we had it here. Sorry.
I think it was like 0.65 or something.
Yeah, exactly. 0.65. And we can see that when we include that ablat covariate, it's reduced to 0.35. So you now you're remember that this is the in the model that I showed to you. This is this plays an important factor. I know. Can you see my screen?
Yes.
I went back to my notes. So this plays an important factor here, right? Because this came down from 0.65 to 0.35. Therefore, these theta I are going to be closer together, right?
I think we're still seeing your R.
Oh my goodness, sorry. So yeah, this can be seen exactly here, right? Because this is smaller, then these theta I are going to be
That saying by adding that covariate explains some of the heterogeneity between.
Yeah, exactly. Yeah, you're in this model right here. It's adding plus mu plus beta x beta ablat, right? beta ablat. Same again, same structure as an GLM. Any questions? Sorry, the topic is too broad, and I tried to do my best under 1 hour. So yeah, I apologize if I was either too fast or then too slow and then too fast again. But yeah, I hope that at least there's something as an introduction. It helps you to, if you're deciding to run a meta-analysis or you have done it and you want to try now Bayesian approach. I hope this helps you to as a startup.
I think I have just one more question.
Yep.
Can you share some like suggestions on how to pick priors for the mean effect and the random effect? Is there any like sort of standard ones that?
So what? Yeah, this is a hierarchical model. So I'm going to show you. This is the stand code that I wrote for this model, and I'm going to show it because for hierarchical, when you have hierarchical models, it is and especially when you have a lot of groups and not that many data, it is recommended that to use to reparameterize your model under it's called non-center parameterization. And basically what it's doing is, because you're sampling, because we're trying to sample, this will help to speed up your MCMC. So what I recommend, for example, for this is a model, right? So what I do, instead of doing mu, give really wide priors or really vague priors for my model, what I usually do for mu and sigma are, and this is the default from BRMS, weakly informative priors, in the sense that you don't expect that your mean effect size is really greater than 3 or 4 or minus 3 or 4, and you also don't expect that your standard deviation is not that big, right, between study variation, right? By default, BRMS uses a student T, and this is because student T has heavier tails, right? So there are more chances that you can sample from the extremes, right? The issue when sampling with heavier tails is that there can be on the posterior a bottleneck, right? There could be a bottleneck, and then it won't explore the whole posterior, your MCMC, or it will take forever, right? So yeah, I will recommend. There's a really nice. I'm gonna stop sharing and share again. Not only for meta-analysis, but if you're working with STAN or BRMS, there's a wiki under their GitHub. Oh, where is it? Let me see if I can GitHub. Where is it? Ah, here it is. Yeah, he should see. No, I want to see it. Yeah, this is the one. So under the STAN repository, there's a wiki about prior choice recommendation, and this is a beautiful blog post about how to choose a prior, right? So yeah, the same for mean effect sizes. It will be something, and it can be usually it's student T or normal, right? And the same and the same for variance. Now you can be, before I forget to tell, the student T distribution as a prior. I don't know what happened to my. But anywho, I'm gonna stop sharing. The student T as a prior can take any positive number, but it is really straightforward in BRMS or in STAN. To use the positive part, which is called half student T, and this is straightforward because in STAN or BRMS you can set up boundaries in your parameters, right? So if I go again, just to finish that, sorry. Yeah, the nice part of STAN is this is STAN model. where is the STAN model? STAN model. STAN. Yeah. The really nice part of STAN is that you can set up boundaries in your parameters. So sigma is my between study variation, right? And I'm under STAN, you can say, okay, it cannot be lower than 0, right? And therefore you can assign even though the student t distribution can take any value, positive and negatives, it will only retain the positives because you're constraining your parameter in STAN, right? So basically, before there was a choice of priors given for give sampling, we were used to using conjugate priors, but now with these new probabilistic programming languages such as STAN or the one in Python that is also Py3MC and Turing in Julia, with all these new PPLs, well, basically we can try now any priors and do sensitivity analysis with a different choice of priors.
Great. Do we have any more questions for Juan Pablo?
I'm gonna copy and paste this.
Okay. Thank you so much. I'll stop the recording.